Welcome to HFCL Time Machine. Past, present, future, all connected.
Let's step into today's chapter, where we explore a really strange, honestly, kind of a multi-billion-dollar paradox happening in the tech world right now.
Yeah, it's definitely catching a lot of infrastructure planners totally off guard.
Right, because, imagine you're a major tech company, right? You just spent tens of billions of dollars getting the most advanced artificial intelligence chips on the planet.
The hardest part, supposedly.
Exactly. You've got the power contracts, you have the actual physical data center buildings, but then you go to flip the switch and your cutting-edge compute cluster is basically just, a warehouse full of incredibly expensive space heaters.
Just burning electricity and doing nothing.
Right. And why? Because you're literally missing the microscopic strands of glass needed to let them talk to each other.
It's wild. It is a profound bottleneck.
It really is. If you look back at, let's call it phase one of this whole AI race, the entire focus was just accumulation.
Right, hoarding compute.
Yeah, it was super loud, wildly expensive, and the only metric anyone cared about was hoarding GPUs. Get the chips, secure the power, build the shell.
Well, because in phase one, if you didn't have the raw compute, you literally didn't have a seat at the table.
Exactly.
But that era is pretty much over. We're firmly in phase two right now, and phase two is entirely about system scalability.
So having the silicon isn't the big flex anymore?
No, not at all. The differentiator now is whether your physical architecture can actually move data between those chips fast enough to keep them fed.
Which is causing this massive ripple effect that frankly just defies normal hardware cycles. The numbers we're looking at are kind of hard to process.
Oh, they're staggering.
The active optical networking market is undergoing this massive 9x expansion right now. We're talking about a market that is roughly $15 billion in 2026, and it's projected to hit $154 billion by 2028.
A ninefold increase, just compressed into 24 months.
Okay, wait, I have to stop and push back on that a little bit. Because, you simply don't see a 9x infrastructure spike just by swapping out some old cables for new ones.
Right.
Standard tech refresh cycles are incremental. A jump to $154 billion means something fundamentally broke in the traditional data center model. What is forcing this kind of unprecedented capital spend right this very second?
Well, what broke is basically our entire assumption about how data actually moves inside a building.
Okay, how so?
To understand why this massive explosion is happening, you really have to look at the physical materials required to build an AI facility compared to, what we've been building for the last 10 years.
The standard cloud data center.
Exactly. To construct an AI data center today, you need up to 36 times more optical fiber than a conventional cloud facility of the exact same physical size.
Wait, I want to be absolutely clear on this. You're not saying 36% more.
No, 36 times more.
Wow.
Yeah, it is a 36-fold multiplier in the sheer volume of glass you have to lay down inside the exact same footprint. That physically doesn't even seem possible.
Yeah.
If you take a standard cloud facility from, say, 5 years ago, it's already packed with servers and cables, right?
Right, they're dense.
So how do you take that same square footage and demand 36 times the volume of fiber optics?
Yeah.
Why is the difference so massive?
It all comes down to traffic patterns. So in a traditional cloud data center, the vast majority of the traffic is what network engineers call north-south.
North-south, okay.
Yeah. So a user sitting at home requests a video, the server pulls it from storage, and it travels north out to the internet.
Got it.
The servers inside the building don't really need to talk to each other that much. They're just serving you individually.
Okay, so they're like independent workers just doing their own separate tasks at their desks.
Precisely. But AI training workloads require a completely different architecture. The traffic in an AI cluster is almost entirely east-west.
Meaning server to server. Exactly, GPU to GPU. When you're training a massive model, you aren't just serving one single request. You have thousands or even tens of thousands of GPUs working on one unified problem.
They're collaborating.
Right. They have to constantly share weights, sync calculations, iterate millions of times a second. So every single GPU needs a direct, essentially zero latency highway to almost every other GPU in the building.
Oh, wow.
Yeah, it requires a density of interchip traffic that the computing industry has quite literally never seen before.
So, to use an analogy here, it's like buying tens of thousands of these advanced GPUs without that optical connectivity. It's essentially like buying a massive fleet of multi-million-dollar Formula One supercars, right?
I like where this is going.
And then forcing them to drive on a single-lane dirt road. Like, it doesn't matter that the car can go 200 miles an hour if the road only fits one vehicle going 10 miles an hour.
Exactly. The chips just stop being your main asset.
They just become idle hardware waiting on data.
That is exactly the dynamic. And, when every major player in the world suddenly realizes they need 36 times more fiber per facility to build these Formula One tracks,
You hit a wall.
you hit a brutal reality. The global supply chain just cannot handle it.
I was actually going to ask about that, because when demand for literally any manufactured good spikes 36 times over, something has to snap.
Oh, it snapped. The math right now is incredibly sobering. Because of this massive architectural shift, global fiber prices rose about 70% between 2021 and 2026.
70%.
Yeah, but honestly, the cost isn't even the primary issue. It's the time.
Right.
Lead times, which is the delay between ordering the fiber and actually getting it delivered to your site, they stretched to a massive 60 weeks in 2026.
Wait, 60 weeks?
60 weeks.
That is well over a year, just sitting in a queue waiting for materials. I mean, if you're an enterprise IT leader listening to this right now and your board is demanding an AI product launch next year, a 60-week delay that's a career-ending bottleneck.
It is the defining constraint on AI deployment right now.
Yep.
Actually, one major global manufacturer literally sold out their entire 2026 inventory before January even started.
That is insane.
It is. And recent surveys show that 91% of enterprise IT leaders admit fiber availability is directly limiting their AI infrastructure plans. It dictates where, when, and honestly if they can build.
So the roadblock isn't TSMC printing the silicon fast enough. The roadblock is getting the glass to connect the silicon.
Exactly.
Which, okay, that leads me to a really basic physical question. Where exactly is all this fiber going? If we're talking about massive 36x multipliers, how does the industry actually categorize where this glass is being laid down?
Sure. So we generally break the networking stack down into three distinct layers. First, you have scale across.
Okay.
This is the network connecting separate, geographically distant data centers together.
Yeah.
And second is scale out. That's the networking across the facility itself, so connecting different rooms or clusters of equipment.
Makes sense.
But the third layer is the most critical right now, and it's the one driving this massive market expansion. That is scale up.
Scale up.
Yeah. Scale up is the networking within and across the individual server racks.
No, wait, I have to challenge you on that last one. Because for decades, the connections inside the server rack, like the cables running mere inches away from the processing chips, those have traditionally been copper.
They have.
Because copper is cheap, it's reliable, it bends easily. So why are we suddenly pushing light through glass, literally mere inches away from a processor?
Well, and it's important to say it is not about demeaning copper. Copper has been an incredible workhorse for the entire industry.
Oh, totally.
But this is purely an objective matter of physical limits. Copper has boundaries when you push it to extreme frequencies. Modern AI architectures demand data transfer speeds of 200 gigabits per second per lane.
Right.
And at those speeds, copper simply maxes out.
What does maxes out actually mean, though, in a physical sense? Like, does the cable melt?
Well, it's really about signal integrity and power. When you push incredibly high-frequency electrical signals through copper, the signal degrades rapidly over very short distances. And we are talking just inches.
Wow, just inches.
Yeah. So to fight that degradation and force the signal through, you have to pump a massive amount of electrical power into it, which causes power consumption to spike exponentially.
And that generates heat.
An immense amount of heat.
Okay, so the laws of physics essentially dictate that you just can't push that volume of data electrically because either the signal falls apart or the power draw becomes completely unsustainable.
Exactly. You hit a physical wall, and that forces a mandatory transition to optical infrastructure inside the rack, practically right next to the chips.
I see.
And this specific scale-up transition, moving from electrical copper to optical interconnects at the rack level, it's enormous. It accounts for roughly 69% of that $154 billion market.
Wow, 69% just inside the racks. Let's pull on that thread regarding power consumption for a second, because if we're pushing light instead of electricity that close to the silicon, it has to impact the power draw.
Huge impact.
Right. And anyone following this space knows that electricity is the other glaring existential threat to AI right now. We literally have facilities that are running out of grid capacity.
Absolutely. And power is exactly what this transition solves. Which brings us to a really incredible breakthrough technology called co-packaged optics, or CPO.
Okay, CPO. How does that work?
So to understand CPO, you kind of have to look at the old way of doing things. Traditionally, you have a processing chip, and an electrical signal runs across a copper trace on the motherboard.
Okay.
Then, at the edge of the board, it hits a pluggable optical module, a transceiver, which converts that electricity into light so it can travel down the fiber.
So you have this middleman. The signal has to travel electrically first, which burns power, and then it gets converted.
Right. Co-packaged optics changes the game entirely. It integrates the optical transceivers directly onto the exact same silicon substrate as the switch chip or the AI accelerator.
Oh, wow.
Yeah, it completely eliminates those traditional pluggable modules at the faceplate.
So to visualize this, it sounds a bit like global logistics, right? Like the old way is like manufacturing goods at a factory, putting them on a fleet of trucks, burning fuel to drive them all the way across town, and then finally loading them onto a cargo ship at the port.
That's a great way to look at it.
But co-packaged optics is basically like moving the international shipping port directly inside the manufacturing plant. You completely remove the truck route, which means you stop burning all that fuel.
That analogy is perfect because the fuel in this scenario is electricity. By putting the optics on the exact same substrate, you're taking the electrical path and shortening it from centimeters down to mere millimeters.
Which saves a ton of power.
Exactly. And the hard data on what that physical change achieves is remarkable. By eliminating that electrical truck route, CPO reduces power consumption from around 15 picojoules per bit down to just 5 picojoules per bit.
Okay, translate picojoules for me in the context of a massive facility. I mean, a drop from 15 to 5 is a threefold efficiency gain, sure, but what does a 3x drop actually mean when we're talking about thousands of server racks?
It is quite literally the difference between a facility functioning or physically melting down.
Really?
Yes, because by 2027, the next generation of server rack designs for AI will require up to 50 times the power of conventional cloud racks.
50 times.
Let that sink in. 50 times the power density in the exact same physical footprint. If we don't switch to highly efficient optical interconnects at the silicon level, these racks will require more power than municipal grids can even supply to a single building.
That's terrifying.
And furthermore, the heat generated by pushing that much data electrically would overpower literally any cooling system we have.
So the physics demands fiber, and the thermal realities of the power grid demand fiber. But, circling all the way back to that supply chain crisis we talked about, there is a 60-week global waiting list for this glass.
Right.
If the entire computing world is just waiting in line, who actually has a structural advantage here? Like, who gets to build their future on time?
Well, when you map out the global supply chain, India actually has a profoundly unique advantage.
India. Okay, how so?
Often, global conversations treat India primarily as, a consumer of AI services, or maybe a favorable geographic location to host the data centers. But from an industry insider's perspective, that misses the deeper structural reality.
Which is?
India has decades of deep domestic optical fiber manufacturing capacity.
Oh, I see. So while other regions are literally waiting on cargo ships to cross oceans, they already have the foundries, the materials, and the factories operating domestically.
Precisely.
Yeah.
And that domestic capacity is incredibly vital because AI is not the only technology demanding this fiber right now.
Right, there's other stuff happening.
The infrastructure strain is a layered problem. Simultaneously right now, you have massive 5G backhaul rollouts happening all over.
Oh, sure.
You have unprecedented rural broadband expansions like the BharatNet initiative connecting hundreds of thousands of communities. And alongside all of that, standard enterprise data centers are also scaling up.
So these aren't competing demands where one project wins and another one loses. They are compounding demands.
Exactly.
They stack on top of each other, putting exponential pressure on the same physical infrastructure pool.
Which is exactly why piecemeal solutions just do not work anymore. You can't solve compounding bottlenecks by buying cables from one vendor and switches from another.
Right.
At HFCL, the realization was that the industry needed a unified end-to-end physical foundation that was specifically engineered for these extreme constraints. So we consolidated 35 years of manufacturing depth into a single ecosystem called Optic AI.
Optic AI. Okay, let's dig into Optic AI. Because earlier you mentioned the physical constraints inside these 2027 server rack spaces that are incredibly dense, extremely hot, and just packed with expensive hardware. How does a unified system actually address those physical realities?
It addresses them by engineering the passive infrastructure, so the glass itself, to meet the exact requirements of the active AI components. Optic AI is built around 5 core design pillars.
Okay, what are they?
The foundation is high quality because AI workloads simply do not tolerate signal degradation. Then you have quantum bandwidth, which ensures the pipes are physically large enough for next-generation speeds.
And what about the space issue? Because if you are putting 36 times more fiber into the same square footage, the routing alone must be a total nightmare.
Oh, it is. And that leads to the third pillar, densely quantified. This is all about maximizing the number of individual fiber strands you can engineer into microscopic spaces within the rack without losing any performance.
Got it.
The fourth is quick rollout, which directly attacks that 60-week delay issue through unified, streamlined deployment strategies.
It's huge.
And the final pillar is Q-class uptime. In a traditional data center, a millisecond network drop is just an annoyance. But in a massively parallel AI training cluster, a millisecond drop cascading across 100,000 GPUs can completely corrupt the entire training run.
Oh, wow.
Yeah, it's a catastrophic failure.
So Optic AI is essentially the nervous system that guarantees the compute brain actually functions. It bridges the gap between the speed that chips want to run at and the physical reality of the data center.
Exactly. It is specifically engineered to support ultra-dense 800G and 1.6T network architectures inside these incredibly tight, power-hungry footprints.
Okay, I want to pivot here and make this highly actionable for the listener.
Sure.
If you're an infrastructure leader tuning in right now and your CEO is demanding a fully operational AI cluster by 2027, but you absolutely do not want to be the person explaining why you're stuck in a 60-week procurement queue, what practically needs to change about your playbook today?
The overarching shift is that you have to stop treating optical fiber as a commodity that you just order at the tail end of a project. It has to be a strategic imperative at the very beginning at the architectural phase.
So design it in from day one.
Exactly. There's a rapid-fire strategic guide we give to leaders, and it comes down to 4 fundamental changes.
Okay, well, let's hear them.
The first one is where most deployments are failing right now. You must specify your fiber grade at the design stage, not at procurement.
I'm going to play devil's advocate here for a second. If I'm a procurement officer trying to manage a budget, glass is glass, right? Like, why can't I just buy the standard telecom fiber that my company has successfully used for the last 10 years?
Because standard telecom fiber, specifically G652D, will physically fail in an AI rack.
Really? Why?
Remember what we said about the density?
Yeah.
The racks are so incredibly packed that the fiber cables have to be bent around very sharp, tight corners to actually reach the GPUs. Standard optical fiber is like a straight pipe. If you bend it too sharply, the light literally leaks out of the glass core and you lose the signal.
Wait, the data literally bleeds out on the corners?
Yes. AI scale-up requires a highly specialized glass called G.657A, bend-insensitive fiber. It's engineered so that even when it's bent around a sharp rack corner, the light remains trapped inside the core.
Wow.
If you design your multi-million-dollar facility assuming standard fiber, you'll power it on, the signal will drop, and you will have to physically rip out and recable the entire building.
Okay, that is a terrifying scenario. So specify bend-insensitive fiber immediately. What is the second change to the playbook?
Designed for tomorrow, not for the speeds you're running today. Right now, 800G networks, meaning 800 gigabits per second, are deploying. But 1.6T, 1.6 terabits is already entering production.
Things are moving so fast.
You must build the passive infrastructure, the physical glass, to handle 1.6T and beyond today. You cannot afford to replace the central nervous system of your facility every 2 years just because the chips got faster.
That makes perfect sense. Just lay the biggest pipe possible once. So what is the third shift?
This one often gets completely overlooked. Backhaul is AI.
Let's quickly define backhaul for the listener. We're talking about the connection from the facility out to the rest of the world, right?
Correct. The backhaul is the fiber connection linking your isolated AI data center to the broader telecom core.
Okay.
A lot of planners treat the AI facility as one isolated project and then the backhaul as a totally separate telecom department issue.
Right. Different budgets, different teams.
Exactly. But you have to stop siloing them.
Mm-hmm.
The backhaul dictates the latency your end users will experience.
Ah, I see.
If your AI model processes a prompt at lightning speed inside the building, but then the response hits a data bottleneck the second it tries to leave the building, your end product feels slow to the user.
It goes right back to the supercar analogy. It doesn't matter how fast the car drives on the private track if it has to exit the facility onto a dirt road. It just ruins the performance.
Spot on.
And what is the final strategy for leaders to adopt?
Count the passive with the active. We talked about that massive $154 billion active component market, the transceivers, the CPO modules, the AI switches.
Yeah.
Every single dollar spent on that active gear sits on top of passive optical fiber. You have to budget, design, and procure them simultaneously. Do not buy billions of dollars of active gear and then wait to source the passive fiber, or you will literally be paying interest on useless hardware while you wait 60 weeks for delivery.
It really reframes the entire conversation around artificial intelligence. We spend so much of our time mesmerized by the algorithms, the software, and the incredible generative capabilities of these models.
This is the glamorous part.
Right. But when you synthesize everything we've unpacked today, it becomes remarkably clear that the physical network is no longer just the plumbing of a data center. It is the absolute foundation that decides if a multi-billion-dollar AI initiative actually functions and if it reaches the market on time.
It truly is. And, if there's a thought you should carry with you after today, consider this. As we push the boundaries of what computing can achieve, and as we watch GPU clusters scale toward deployments of 100,000 chips or more, the ultimate speed limit of human AI development might not actually be decided by the silicon engineers designing the chips.
No.
It's increasingly likely to be decided by the material scientists figuring out how to push infinitely more light through a microscopic strand of glass.
And that brings us to the end of this chapter in the HFCL's Time Machine. Until next time, stay connected to what's next.
You've been listening to HFCL Time Machine. For more conversations like this, find us on LinkedIn, Instagram, and YouTube.